Hello class, welcome to this lesson on 5.3. We're going to be talking about all about graphing radical functions. So how can we use what we know about transformations of functions from the earlier units to graph radical functions? So our learning goal is to be able to graph and transform radical functions. So we want to know about what a radical function is in order to graph it here. So remember that a function is simply a machine that takes an input and spits out an output. So we're going to look at graphing a square root and a cube root function. Here, in this case, we usually have an f of x to indicate that it's a function. So we input an x and then we get a y from that. And then we graph that as a coordinate on the coordinate plane. So in this case, I'll just call that f of x and I'll call this g of x. It's important to know that f of x and g of x are simply just y. So this is just, stands for y. Okay, so in this case, we want to set up an x, y table in order to be able to graph these two functions together. Okay, so this is the most basic function, square root of x and then cube root of x. These are known as the parent functions, and this will be our model for the future transformations in this lesson. So, if we want to graph the square root of x, well, first let's pick some values for that work for x. Remember that we cannot take the square root of a negative number here, so negative numbers are out of the question as far as this function is concerned. So we can use 0, we can use 1, we could take the square root of 2, but that would give us a decimal. So let's use a number that is nice here. So let's use square root of 4. And then we'll use one more, square root of 9. And then of course you can go square root of 16, which I guess we could put here just for the sense of having that extra number there, but we're not going to really graph that. So if we plug in 0 as the input into this function, well, we know that the square root of 0 is 0. And we know if we put input x as 1, well, we know the square root of 1 is 1. And then we know the square root of 4 is 2. And then the square root of 9 is 3. Square root of 16 is 4. So now we have a set of ordered pairs that we can go ahead and graph. We have our x and our y-axis. So we have in our origin 0, 0 here. All right. And then we have our coordinate 1, 1. So let's say this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 9. That's 1, and then we'll call this 4. So we have 1, 2, 3, 4. So we have 1, 1 as a coordinate. We have 4, 2 as a coordinate. And we have 9, 3. And so we should be able to graph this. It looks like it continues in that direction, and it goes, it's going slightly upward. And that's our function for the square root of x. Now, if we were to do the cube root of x, we're going to need to choose some other numbers as well. Now, you can have negative numbers here for the cube root of x, because you could take the cube root of a negative number. So, for instance, we could take the cube root of negative 8, because we know that negative 2 times negative 2 times negative 2 is negative 8. So this works out. So this is going to be negative 2. So if you input negative 8 into the cube root, well, we know that the cube root of negative 8 is negative 2 because of the above. Similarly, we can put negative 1. The cube root of negative 1 is negative 1. The cube root of 0 is 0. 0 times 0 times 0 is 0. The cube root of 1, 1 times 1 times 1 is, 1. The cube root of 8. So the cube root of 8 is going to be positive 2. Positive 2 times 2 times 2 is going to be 8. So this is going to be positive 2. All right, so now we got our coordinates. We can go ahead and plot those. All right, so we have here When x is 0, y is 0. When x is negative 8, y is 2. Or negative 2, I mean. When x is negative 1, y is negative 1. When x is 1, y is 1. When x is 8, y is 2. So we get something that kind of looks like this on the bottom, and then it goes up and like this. Okay, so it's kind of like a reflection on both sides of the origin, but it's, you know, growing at a less, I guess you could say, a less steep pace than it would for the square root. But it has two sides to it, unlike the square root, which has the one side. All right, so that's how our graphs look like. That's how the basic function looks like. So now that we know how the functions look like, they're also given in these two graphs. We have the square root of x on the left side, the cube root of x on the right side. So they have that characteristic shape. So just keep that shape in mind whenever you're doing the graphs. So if I were to ask you what the square root of x looks like, well, it just looks like that. You just have to picture that in your mind. Same thing with the cube root of x, picture that in your mind. Now, so these are known as the parent functions. So if we transform those functions, they'll look like below. They can take on those forms where a, h, and k can be any number for these functions. We're going to talk about what a, h, and k do to each of these functions right now. So in order to demonstrate this, we're going to show you the graph of square root of x first on Desmos. Okay, so what we're going to do here is we're going to zoom in, try to zoom in on this here real quick so you can see the graph. So right now we have the square root of x, which looks like that. So now notice what happens if I introduce a term, if I introduce an a term in front before the square root. So we're going to go ahead and introduce an a term before that square root. All right, so we got an a term. We're going to add a slider here. So now when a is 1, the graph, oops, that's the wrong thing here. The graph looks like, normal. Now, if we let the a become positive 2, then notice what happens to the graph. The graph actually grows quite a bit, so it goes up, right? So the shape of the graph is the same, right? It's in the same direction and so on, but it's we call this vertically stretched because it's stretched up, almost like a rubber band. If you were to take this and kind of stretch it up, it would look like that. It was stretched up, it was vertically stretched by a factor of 2. Now if I take this 2 and I change it to a -1. So notice what happens as it goes down, it starts approaching the original function. As it goes up, it starts getting more and more and more stretched, right? Then if you go onto the other side, if you become a fraction, let's say less than 1, then what's happening now? Well, now this graph is being compressed. So instead of it being stretched up, it's being pushed down, and we call that a vertical compression. It's being compressed downward in the y direction. And then if we go to the negatives, well then now it's starting to be reflected, right? We can tell now it's being reflected. It's being reflected about the x-axis. And then if we're more into the negatives, -2 and so on, -4, well it's being reflected, let me go back, it's being reflected, but then it's being stretched in that other direction, right? So it's basically a combination of two different transformations, a reflection and a stretch. So we're going to go ahead and write this down for a, right? So for a is basically a vertical shift or vertical compression or stretch rather. So a deals with reflection and vertical, what we call vertical stretch or compression. So that's what a does. So like we mentioned earlier, if a is bigger than 1, like 2, then this means that we're going to have a vertical stretch. It's going to stretch it up like a rubber band. Now if a is a number that is between 1 and, say, 0, then this means that we're going to have a vertical compression. And we're going to go ahead and say that this is the absolute value of A. Okay, so basically we'll say that when A is positive and it's between 0 and 1, then we call that a vertical compression. Now, if A is negative, so if A is less than 0, which means it's negative, then we have a reflection about the x-axis. Just like we mentioned earlier, this is a reflection, this is the x-axis here, right? This is the x-axis, and it's being reflected about the x-axis there. So if this is the graph, it's being reflected this way, right? So it's a reflection about the x-axis. All right, so that's what A does. Now let's take a look at H. All right, so let's go ahead and take a look at the function. Now, instead of having an A here, we're going to change this. And we're going to say we're going to add an H there. Okay, so notice what happens if H is 1. If H is 1, then looks like the graph has been shifted over to the left by 1. So H seems to shift it to the left if H is a positive number, or yeah, if H is a positive number. Now, if H were to be a negative number, like -1, then in that case, it shifts it to the right instead. So if H were negative, shifts it to the right. If H were positive, shifts it to the left. So that's what H does. Actually, now in this case, now that I think of it, this formula is x minus H. So that's going to change things a little bit. So let me change this to a minus now this time. Now, because the formula is now minus, the double negative makes it into a positive, right? X minus -1 makes it positive. So if I change it to -1, now it actually shifts it to the left. So the moral of the story here is that normally it's x minus H. If H is negative, in this case, it's going to shift it to the left. And the reason being is that if H is negative, then you're going to have here x minus -H, and two negatives make a positive, right? So it's really x plus H. However, you instead of saying that this goes to the right, you say that it goes to the left, okay? So if H is negative, it means left. Now, if H were positive, right, and the formula is x minus H by default, well, then this is still going to stay minus H. So if H were 2, for instance, this would be x minus 2. In that case, this sign becomes negative, right? That sign here, it becomes negative. And so that means to the right. So it's kind of like opposite of what you think, right? As far as that sign is concerned. But as far as H is concerned, if H is negative, then it goes left. If it's positive, it goes right. So you just got to be very careful with how you do that. Okay, so we're going to go ahead and finalize this here for H. So if H were positive, right, meaning that it's greater than 0 means positive, okay? Then this means that we have a shift to the right. If H is negative, if H were negative, then we'll have a double negative here, making this into a positive, and that would make it shift opposite of what we think. So instead of right, it'll be left. So it'd be shift left. Okay, so that's what we got for H being positive or negative. Now let's look at the plus K. So we're going to go ahead and change this now to a plus K on the outside. So now notice what happens if K is 1. If K is 1, it shifts the graph up 1. If K were to be negative, let's say -1, then in that case it shifts the graph down. So the K stands for the vertical shift. K is pretty straightforward. K is positive. Then it's a shift up. If K is negative, it's a shift down. All right, now there's one more thing that is not actually written in this form, which is kind of strange that I forgot, that the textbook actually forgot to include this, but sometimes there will be an extra term here. We're going to call this a B term. Okay, so go ahead and adjust your notes for this. So it's not in the textbook, but it's an actual textbook problem, so it's very odd that it wasn't included, but there it is. So sometimes they'll have an extra term there, and I'll call that B. All right, so just because we have A and then B. All right, so there we go. So we got another term called B. Now there's that multiplier there that's on the inside. That multiplier changes things as well, right? So instead of it being a multiplier on the outside, it's a multiplier on the inside. So let's see what that does. And that would be the last thing that we're looking at here as far as transformations are concerned. So now let's change this to a B on the inside. All right, so what happens if B is 1? Well, if B is 1, it doesn't do anything because 1 times x is x. So if you look at it, nothing changes, right? It's just the original graph. Now, if I change this B to a, say, positive 2, what does that actually do to the graph? Well, it turns out that having a number in there tends to actually do a couple of things. You can think of it as a vertical stretch, or you can also think of it as a horizontal compression. So what's actually happening here is that you're taking this graph and you're compressing it in the x direction. And when you compress it in the x direction, it goes from this and you're pushing it, and so the graph ends up going, like this. When you're compressing it, is being compressed in that direction. So it's getting smaller in the x direction. So as it gets smaller in the x direction, it kind of blows out in the left direction. So this is actually a horizontal compression. It's kind of hard to tell, right? So how do I know that's a horizontal compression? Well, take a look at this point right here. This point is 1, 1. So we know that the y-coordinate is 1. Now we know that the y-coordinate here is also 1. But take a look at the x value. The x value turned from a 1 over here. It's kind of hard to do this. It turned from a 1 to a 0.5. So it went from 1 to 0.5, which means that it got compressed by a half. If you're going from 1 to 0.5, that means you got reduced, right? We got reduced by 50%, by 2, basically. So this is a vertical or a horizontal compression, okay? So if B is greater than 0, greater than 1, greater than 1, it's a horizontal compression. You can also think of it as a vertical compression, or vertical stretch, sorry, because it kind of looks like a vertical stretch as well. So it's being compressed horizontally, but you can kind of tell it's being stretched vertically as well. So it's kind of both. All right, but we refer to it as a horizontal compression. Now, what happens if B gets smaller? So like a number between 0 and 1, like for example half. Well, in the case of half, well, notice that the graph actually went more to the right, right? The black is the original, the red is the new. So it actually got horizontally stretched, right? So it got stretched in the x direction that way. So therefore, if the graph started out like this and you stretch it, well, then it's gonna stretch like that, right? If you stretch it in that direction. So x is getting larger. You can also think of this as a vertical compression. So notice what happens. The original value, when the y value is 1, the x value is 1. Now, when the y value is still 1, the x value changes to 2. So the x value changed from 1 to 2, which means it got stretched from 1 to 2. It got stretched by a factor of 2, because 1 times 2 is 2. So therefore, we call that a horizontal stretch. This is probably the hardest concept to kind of understand, and it takes a little while to get used to the idea of horizontal stretch or compression. But notice that the horizontal stretch here is the same thing as a vertical compression, but it's a vertical compression in a different kind of way. So we can also think of as a vertical compression. All right, so now what happens if b is negative? This is the very last case that we got to look at. So if b is negative, let's say a negative 1. Let's change that to negative 1. Well, in that case, look what happens to the graph. The graph actually reflects. It reflects about the y-axis. You can kind of tell. So if b is negative, which means that it's less than 0, then we have a reflection about the y-axis. Okay, so I kind of went over this just to kind of review the transformations, because it's been a while since we've done these transformations. So just kind of keep that in the back of your head whenever you're trying to do these problems. This is what these different things do. However, it'll be kind of apparent. You don't actually have to know per se what each of these things do, because it's kind of evident in the graph when you actually graph it. So as you graph it, you'll kind of see, well, okay, this is what it does. But I wanted to actually just list those out so that you have them. Okay, the same deal happens with the cube root of x. The exact same transformations happen. So for instance, if I want to reflect this about the y-axis, well, now all I have to do, let me zoom in on this graph here real quick. If I want to reflect this about the x-axis, well, then I just have to put a negative out here. And see, now it reflects this about the x-axis. Now I'm going to do this to a different function here. So I'm going to write another one here. Okay, so that way you have it in red. So now if I put a negative there, then it reflects it about the x-axis like that. If I want to reflect it, if I want to vertically shift it, then I'm going to add 2 to it, and that's going to shift it up like that. If I want to shift it to the left, then this is going to be a plus. Okay, so if I want to shift it to the left, it's going to be plus 2. Let's say I want to shift it left 2, then that has to be a plus on the inside. That's kind of opposite of what you would think, right? You would think plus is to the right. But when you're talking about the x transformation, which is on the inside, then it's actually opposite. So plus is left and minus is to the right. So I'll show you if we did a minus 2, that would actually be shifted to the right. Okay, but when you're talking about, for example, a transformation that is on the outside, then it's exactly what you think. Minus is down to the ground and plus is up to the sky. All right. Also notice there's a couple of other things that I want to make sure that you see, so that you understand, is that when you're talking about horizontal stretches, if I put a 2 out here, then that's going to stretch this graph by a factor of 2. So this graph will be 2 times bigger than when it originally was. So if this coordinate here were, if this were the coordinate, let's say 1, right? Then it's going to be multiplied by 2. So in this case, this y value will now be 2. So it's 2 times bigger. Now if I do this to, for example, the x, right? If I multiply the x by 2, then look what happens. If I multiply the x by 2, then now the graph actually gets compressed by a half. So instead of being multiplied by 2, it's actually being divided by 2. And I'll show you why that is. So if you look at the y value, or the x value here, the x value is 1, right? 1 comma 1. And if I look at the same y coordinate, which is over here when y is equal to 1, look what happens to the x. The x got cut in half. So the x went from 1 to 0.5, which means that you divided it by 2. So it's the opposite of what you think. So instead of it being a times 2 transformation, it's actually cutting it in half. So this would actually be a horizontal compression by a half. So something to keep in mind, and we're going to actually add that to the transformations here. So when we're talking about b's, this is going to be a horizontal stretch by a factor of 1 over b. And then the same thing here, horizontal compression by factor of 1 over b. So basically you just kind of do the reciprocal. So if it was a half, it would be a 2. If you are doing a compression by 2, it's really dividing it by 2 instead of multiplying by 2. Alright, so I know that's a lot, but we're going to actually show you how to graph this. So that was just the basics of transformations. Stuff that applies to any kind of function, not just square roots or cube roots. But how do we actually graph it? So if we want to graph this, then we're going to first keep in mind the parent function. So I know that the parent function of this looks something like this, right? Just like we drew before, where it starts at the origin and then goes up like this. That's the parent function. So this should look kind of like that. Now the 9 is going to do some kind of multiplying effect. All right, so we know it'll look similar to this. So how do we go about graphing it? Well, what I do is I use what I call an XY table, a special type of XY table. So I have XY, and I have here what I call my X transformation, and then I got my Y transformation here. Okay, so this is my X transformation. This is my Y transformation. And then this will be evident, when we do this, when I go over it with you just right now. Okay, so hold on to this for a little bit. We'll get to the X transformation and the Y transformation in a little bit. Okay, so first off, the parent function for this is square root of X. So what I'm going to do is this Y is going to be equal to square root of X. So I'm going to label this as Y, and I need a little bit of room here. Y equals square root of X. Okay, so now what I'm going to do is I'm going to pick the values that I chose earlier. Remember that the nice values that we chose when we graphed square root of X? Well, that included 0, 1, 4, right? And also 9. We chose 9, and we also did 16, but 16 is kind of big, so we're going to stay away from that big of a number. So we're gonna, when we did this earlier, we know that the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, and the square root of 9 is 3. So we got those nice numbers. This was straight from the other table. I'm not doing anything new here. Okay. Now we know that the function is not square root of x; it's actually square root of 9x. So how do I account for that? Right. So what we know here is that whatever the x is, we're multiplying it by 9, right? So we're gonna put that in our transformation. So here's what we do. If it is an x transformation, this is an x transformation because it's multiplying the x directly. What I'm going to do is I'm going to set that equal to x and solve. So I'm going to call this, let's call this x prime or something like that. I don't know. And something to distinguish, to make this look different from the 9x here, okay? So that way we're not confusing the x prime with the x here. So what we're going to do is we're going to solve for x in this equation. And the only way to solve for x is to divide by 9, right? Okay, there you go. So now we got x in terms of this. So now what we're saying here is that instead of multiplying by 9, we're really dividing by 9. So we're going to take this transformation and put it in our table. So we have here, we're going to just call this x over 9, since this is our x prime here. This is our transformation. Notice I'm not writing the prime there, I'm just writing that as x, because now this is our new x. So that means that we need to take our original x and divide it by 9. Alright, why are we dividing it by 9? Well, the reason why we're dividing it by 9 is because the x's are kind of like opposite of what you think. If you're doing something to x, it's really the opposite effect on the graph. Alright, so for the y's, what about the y's? Do we have any y transformations going on here? Well, the answer to that is no, because there are no transformations being done to the radical itself, right? There's no number on the outside here, there's no number on the outside here that is doing anything to the radical. So the answer is no, there's nothing that is, there's no y transformations here. So nothing is being done to the radical, which means that the y is not being transformed at all. So I'm just going to call this y. Alright, can be a little confusing at first, but as we do more problems, you'll get the hang of how this transformation works. So now when we have x equals 0, then we have here 0 divided by 9. And we know that 0 divided by 9 is 0. And since the y transformation did not change, we're going to be using the same value here. And we're just going to rewrite it there. Alright, so basically these y values are the same because they're not transformed. These x values will change though. So we're going to take this x equals 1 and plug it in here. And in that case we get 1 divided by 9, which is just going to be 1/9, right? So there's nothing that we can do there. It's just going to be a fraction. Next we're doing x equals 4, plugging that in there, which becomes 4 over 9. And then lastly, we're doing 9 divided by 9. Well, we know that 9 divided by 9 is equal to 1. Alright, so we got here, let's go ahead and clean this up. So this is now equal to 1, this is 4/9, this is 1/9, and this is 0. Alright, so again, you don't have the advantage of rewriting this, but the reason I'm rewriting this is just to make it look nice. Alright, so those are my new coordinates. So we have our old coordinates being transformed into these new coordinates. Okay, so this means that we're going to be plotting these coordinates here into the graph, into the coordinate plane, and then we should be able to get our transformation. Alright, so let's go ahead and start. So we got 0, 0 is, and let's label our x-axis. So we got all the way to x equals 1. So let's see here, we got x equals 1 and 2, and then we got y all the way to 3. Here, let me go ahead and undo that. Okay, so -1 and -2. So we have 0, 0. And we have 1/9 and 1. So how do we do 1/9? 1/9 is a very small number, right? So we're just going to approximate it, saying that it's very close to 0. 1/9 is about 0.1. So we're going to say it's about 0.1 and 1. 0.1 and 1. So like around there. Alright, 4/9 is actually very close to a half, because 4/8 is a half, right? So this is actually pretty close. This is a little bit over a half, a little bit under a half, I mean. So we're going to go to a half and about 2. And then lastly we have 1, 3. So we're going to do 1 and 3. Now we can go ahead and graph this. And it looks like it's growing pretty high, right? It's going pretty high at first. So it'll probably look something like this. So basically it's continuously growing. So it probably looks something like this, right? If we were to continue it, but we're going to need more points for that. But it'll look something like that. Alright, so what happened to the graph? Well, what happened was, if you look at the original function, normally the parent function will look something like this, and I'll do it in red just so that you can get an idea of how the normal function looks like. Let's see here. Function, okay, so this is how the normal parent function looks like. 1, 1, 2, 3, 4. Okay, so this is how it's kind of hard to tell with these points, but this is how the normal parent function looks like. So it kind of grows like this, right? And it goes like that. So what happened is like the graph actually got compressed horizontally. So I compressed it and I kind of pushed it over to the left. It got compressed by a factor of 9 actually, because here the value for the x is 1, and then here the value became 1/9. So notice that I took the 1 and I divided it by 9 to get 1 over 9. So it got compressed by 1/9. So this is a horizontal compression by 1 over 9. That's what happened here. And that's exactly what we were saying earlier, is that if you got a number here multiplying the x, it's sort of like the opposite, right? Instead, if it's 1 over b, right? So it's 1 over 9. This is like our b term. So it's kind of like opposite. So you flip it. All right, so that's what happened there. So now let's look at our next graph. So there's a lot going on here. Now notice we're going to write out the form that we had earlier. The form that we had earlier was where we had an a term here, we had a b, and then in parentheses we had x minus h, right? So notice that we had this in parentheses. This is important because this means it has to look like this in order for us to use the transformation, okay? So you have to pull the b out. So if there's a b there, you got to pull it out. So that's exactly what we're going to do here. There's a 4 here. Let's pull that 4 out, okay? So if we pull that 4 out, we're going to have to factor it, right? So we got square root 4 parentheses so that it looks like this, right, with the 4 on the outside. And then 4 times x is 4x, and then 4 times 4 is 16. So this is 4 times positive 4. So this gives us 4x plus 16, and then plus 7. Now it looks more like this, right, where we have the b on the outside, and then the h, and then the k. So now this looks like what we need. Okay. So in any case, you can kind of tell now that this is a transformation happening where we have the 4. Okay, so if you don't like doing this, then that's okay. We could still figure this out. We could still figure out what's happening here. Okay. So if you don't like this, then we'll show you another way. All right. So let's go ahead and draw our XY table. We have our x transformation, we have our y transformation. Okay, so again, we're dealing with the square root, so our parent function is square root of x. So we're going to use the same exact values that we used earlier. Oops, that should be a 4 and then 9. These are going to be the same as it was for the other one. Okay, so now, what's our x going to be? Well, let's look at our x transformations. What we do to find the x transformations, remember, what we do is we set the inside equal to x prime. We'll call it x prime. So you can choose either one of those in order to convert it to x prime. So let's choose the one that we factored. So we get x prime equals 4x plus 4. Okay. Now we're going to solve for x here. So in order to solve for x, we're going to divide by 4 to get rid of that. So we have x prime divided by 4 equals x plus 4. And then we're going to subtract 4 on both sides. So we got x prime divided by 4 minus 4 equals x. All right. So we're going to go ahead and use this as our transformation for x prime. We're just going to say x over 4 minus 4. Okay? All right, so that means we take the original x and then we divide it by 4 and then subtract 4. Okay, so that's basically how we deal with those. What about the y? The y's are actually the easiest ones to do. In this case, there's nothing happening to the radical except for the plus 7. That's the only thing that's doing anything to the radical, right? The rest is actually inside the radical, so it's not doing anything to it. The only thing that's doing anything directly to it is what it's on the outside. So therefore, we're just going to do plus 7, right? So we're going to take our y value, and we're going to add 7 to it. All right, just to give you an example, if there was a 2, if there was a 2 outside here, then this would be 2y plus 7, because we're multiplying the y by 2. Again, you can think of all of this as y, right? All of that stuff as like a y. All right, so we got y plus 7. So now, what's going to happen? Well, when x is 0, we're going to plug that in here. So x is 0, x is 0. So we got 0 divided by 4 minus 4. That's equal to 0 divided by 4 is 0. 0 minus 4 is negative 4. 1 divided by 4, we got to put the 1 in now. 1 divided by 4 minus 4. That's going to be negative, you could put that in the calculator, that's just going to be negative 3.75. All right, and we got 4 here, plug that in, we got 4 divided by 4 minus 4. 4 divided by 4 is 1, 1 minus 4 is negative 3. Now let's do 9. We got 9 divided by 4 minus 4. So 9 divided by 4 is 2.25 if you were to do that in the calculator. 2.25 minus 4 is negative 1.75. All right. So we got our numbers here. All right, I want to double check the calculation there. Make sure everything's good. Okay, so we have everything set. So now we got our x coordinates, and let's do our y coordinates. So now for the y, we're going to plug in 0 in there, right? So 0 plus 7 is 7. 1 plus 7 is 8. 2 plus 7 is 9. 3 plus 7 is 10. Very easy for the y coordinate. So now we have our new coordinates, which I will put in parentheses. Let's go ahead and graph these coordinates now. So when x is negative 4, y is 7. So let's see here. We got negative 1, 2, 3, 4. And then we have y all the way to 10. All right, let's go ahead and label these. Okay, so we have here, when x is 0, y is 0. When x is 1, y, or I'm sorry, I'm looking at the wrong coordinates. Sorry about that, guys. Here, let me get rid of that. Looking at the left side. I want to look at the right side here. So when x is negative 4, y is 7. So when x is negative 4, y is 7. When x is negative 3.75, y is 8. When x is negative 3, y is 9. And when x is negative 1.75, y is 10. All right, so we're able to graph this now. So it looks something like that. So again, just to graph our parent function should look something like this. So what happened to our parent function? Well, if you look at it, it looks like it got shifted to the left, right? It got shifted to the left 4, which makes sense because of that plus 4 there. It got shifted to the left 4, right? Plus means left. Now you know why I transformed it so it looks like this, so you can kind of tell, well, okay, well, that got shifted to the left 4. And then the 4 here indicates that it got horizontally stretched or compressed. In this case, it got horizontally compressed because it looks like, this looks like kind of like this, right? Before it got shifted, so it got horizontally compressed. So that's why it looks like that. And then the plus 7, it got shifted up 7, right? So it got shifted 1, 2, 3, 4, 5, 6, 7. It got shifted up 7 because of that plus 7. So we got all the transformations here. So basically, if you're able to do this table, you're able to account for all the transformations. Let's look at some more. So let's go ahead and set up the XY. Now that we kind of have a handle on this, we should be able to kind of fly through this quickly. So let's look at the XY table, just like before. We'll say y equals square root of x. We're going to do our transformations now as well. So these are going to be the same numbers, right? So 0, 1, 4, 9, 0, 1, 2, 3. Okay, so now x prime, let's do that first. So we're going to set this equal to, I guess you can call it x prime. I don't know, I just call it x prime just so that it looks different from the x. And then I'm going to subtract 5, and I get x prime minus 5 equals x. So basically x minus 5 is my transformation. Okay, so I got x minus 5, all right? We're going to plug that in there. And then for the y prime, the y prime is very simple. The only thing you're doing to this radical is you're multiplying it by -3. So there's our transformation, -3. Okay, so it's -3 times the y. All right, so there's our y transformation. So when x is 0, we get 0 minus 5 is -5. When x is 1, we get 1 minus 5 equals -5. When x is 4, we get 4 minus 5 is -1. X is 9, we get 9 minus 5 is 4. Now let's do our y's. When y is 0, -3 times 0 is 0. Now when y is 1, -3 times 1 is -3. -3 times 2 is -6. -3 times 3 is -9. Now we have our coordinates. We can go ahead and plot them, make our graph. So we have here -5. Oopsie, this should be a -4. 1 minus 5 is not -5. 1 minus 5 is -4. So go ahead and make that adjustment there, -4 instead of -5. Okay, so we got -5 all the way to -9 here. We got all the way to -1, 2, 3, 4, 5. All right, so -5, 0. We have -4, -3. We have -1, -6. We have 4, -9. It's around there, and this is our 4 right there. All right, so in this case, our transformation looks something like this. It's actually going more like that. There you go. All right, so what happened to our graph? It looks kind of different, right? Well, the normal graph looks like this, right? So what happened, it got reflected so that it looks like this, right? And then it got shifted to the let's see here. It got shifted to the left by 1, 2, 3, 4, 5. And that's because of this plus here. Remember we told you that this means opposite? Instead of it being to the right is left? Well, that's because of this. So this means left. Okay, so it went left 5. And then it got reflected. That's what the negative there does. It reflects it. And then the 3, it got compressed even more. It got stretched even more. So if it's normally like this, it got stretched out so it looks like this by a factor of 3. So that's why it looks the way it does. All right. Let's look at our next graph. All this takes a lot of practice, but once you get it, it's actually not so bad. So we got x, y, we got our transformations. So this is still going to be square root of x because we're dealing with a square root here, right? Instead of a cube root. So we have the same numbers here. Alright, so x prime, we're going to set this equal to x prime, so x prime is negative x. So basically we're going to divide, this is a negative 1, so let's go ahead and divide by negative 1 on both sides. So this is x prime divided by negative x is just negative x prime. So basically it flips to x prime, so it's negative as well. So in this case it's going to be negative x, alright? So that's our transformation, it's just going to make it negative. And then our y prime, well, y prime is going to be, well, what are we doing to the radical? We're just multiplying it by a half. So basically we got a half y. Alright, so now we have when x is 0, negative 0 is just 0. When x is 1, plug that in there, we get negative 1. When x is 4, plug that in there, we get negative 4, negative 9. So it just makes it negative. And then what about the y? When we plug in y into there, we get 1 half times 0 is 0. 1 half times 1 is 1 half. 1 half times 2. 2 is the same thing as 2 over 1. Multiply straight across, that's 2 over 2, which is 1. If we were to do 3, then 1 half times 3. 3 is the same thing as 3 over 1. Multiply across, we get 3 over 2. Alright, so we got our coordinates here. I'm going to go ahead and circle these so that I can use those as my y coordinates. That's the only reason I'm doing that. So we have here 0, 0, negative 1, 1 half. Let's go ahead and graph this. Alright, we have all the way to negative 9 here. 1, 2, 3, 4, 5, 6, 7, 8, 9. We have here 0, half, 1, and 3 halves. Okay. Okay, so when we have 0, 0, we have negative 1 and then a half. We have we have negative 4 and then 1. We have negative 9 and then 3 halves. 3 halves is just 1 and a half. So negative 9 and 1 and a half. So we have something that kind of looks like that, and there's our graph. So what happened there? Well, it got reflected, right? So it got reflected about the y-axis, because normally it looks like this, right? But it got reflected. And the 1 half. So basically, normally the graph looks kind of like, here, let me see if I can draw this to scale. Normally the graph looks like this. So it looks like it got shrunk, right? It got shrunk. So it got vertically compressed by a factor of 1 half. And then it got reflected. So we got a vertical compression going on here. So hopefully you can kind of get the idea of what's happening to the graph as I'm illustrating it to you with the graphs and the numbers here. All right, let's go ahead and do some examples with the cube root, so that way you have some example of those under your belt, and then we're going to go ahead and have you try some examples. All right, so let's go ahead and get through this. Now we know that we have a cube root here. So that means our parent function is going to be cube root of x. So let's go ahead and set up our xy table per usual, but this time we're going to be using the cube root of x, okay, instead of the square root of x. Again, the transformations are going to work the same, however, the same idea anyways. Okay, so we're going to go ahead and choose our values for x. Now remember that in the slide where we were doing the cube roots, we chose the following numbers. We chose negative 8, we chose negative 1, we chose 0, 1, and 8, right? So I'm going to do the same thing here. I'm going to choose those 5 numbers just so that we have a nice looking graph. Alright, so we said earlier that when we plug in negative 8 into the cube root, that gave us negative 2. If you don't believe me, go back to that slide and you'll see that we had negative 2 there. The cube root of negative 1 is negative 1. The cube root of 0 is 0. The cube root of 1 is 1. And the cube root of 8 is positive 2. Alright, so now those numbers are going to be the same for any cube root type of function. So now the x primes and the y primes, kind of like before, we're going to set this to x prime and then solve that. So it's very easy. You just got to subtract 2 on both sides. So it's going to be the x value subtract 2. So that's what we're going to do here. The x value subtract 2. And then the y value, you're going to just, well, is there anything that's happening to this graph on the outside? Nothing is being done to this radical, so the transformation is simply going to be y. All right, so when we're going to plug into x now. So when x is -8, then -8 minus 2 is -10. When x is -1, well then -1 minus 2 is -3. 0 minus 2 is -2. 1 minus 2 is -1. And 8 minus 2 is 6. Okay, so we got our numbers here. For our y value, the y is going to remain the same. So this is going to be -2, the same numbers here. -1, 0, 1, and 2. All right, so we got our new coordinates here. These are our new coordinates that we're going to graph. So we have here -2, -10, -2. So we got to go all the way to -2, -10. 1, 2, 10, -10. All right. We got a positive x, a positive 6. So we'll do that there as well. And then we got some negative y values and some positive ones. So let's stretch those out a little bit. 1, 2, 3. 1, 2, 3. All right, so let's go ahead and graph this. So we got -10, -2 over here somewhere. We got -3, -1. We have -2, 0. And we have -1, 1. And lastly, it looks like we have 6, 2. All right, so we should have enough to make this graph. So it looks something like this. All right, so there's our graph. Remember that the normal square root function, we're going to go ahead and draw the square root function. Normally the square root function looks like the cube root of 8 is 2, so normally it looks like -1, -1, and then -8, -2. So normally the parent function looks something like that, and so that's our transformed in black. So if we look at the transformations, well, what happened? Well, it looks like it got shifted. It simply got shifted to the left 2, which is exactly what happened. It got shifted to the left 2, and that's because of this plus. So the graph looks the same, except it's kind of shifted to the left, and then that's about it. Okay. Of course, the red is not drawn to scale because I'm not doing it as a perfect graph, but you can kind of tell it's shifted to the left too for the new graph. All right, so let's go ahead and do the last one together, and then you guys will be on your own for the next 2 problems for a little bit. So we have here another cube root function. So we got x, y equals cube root of x. We got x prime, y prime. All right, so we're going to choose the same values as in the table earlier, -8 to a. All right. So let's look at our transformations in the x direction. Well, this is what's happening inside the radical. So that's the x transformation. So we're going to go ahead and set that equal to the x transformation, and we can figure out what to do to this transformation in the x direction. So we're going to solve this for x here. So we got to add the 3 to both sides first. And then we got to multiply, get rid of that 2, that division sign. So we're dividing by 2 here. So we're going to multiply by 2 to cancel it out. So we're multiplying this whole thing by 2. All right, so then if you look at it, right, well, it looks like we're multiplying x by 2, and then we're shifting it to the right 3. So that's basically what it looks like we're doing here. We're doing this transformation here. All right, so I'm just going to go ahead and write that out here. So we got 2 times x plus 3. That's what we're really doing here. All right, and then for our y prime, what are we doing to the outside of the radical? Right, this is the radical here. What are we doing to the outside? Well, we're doing this, right? We're subtracting it by 2. So this is going to be whatever y is minus 2. All right. So now when x is negative 8, we're going to go ahead and plug those numbers into here. So we got 2 times negative 8 plus 3. Well, negative 8 plus 3 is negative 5. Negative 5 times 2 is negative 10. So we got negative 10 there. Now let's plug in negative 1. Negative 1 plus 3, I'll try to write it out just so you have it. Negative 1 plus 3 is 2, and then 2 times 2 is 4. So this becomes 4. And then we're going to repeat. So 0 plus 3 is 3, 3 times 2 is 6, 1 plus 3 is 4, 4 times 2 is 8, 8 plus 3 is 11, 11 times 2 is 22. Wow, that's a big number. So we're going to have to make some room for that. All right, so now we're going to take the y value and minus it by 2. So negative 2 minus 2 is negative 4. Negative 1 minus 2 is negative 3. 0 minus 2 is negative 2. 1 minus 2 is negative 1. 2 minus 2 is 0. So we got here our transformed coordinates, and we're going to graph that. So we got negative 10, so we got negative 10 on the left side all the way to 22. That's a lot. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3. A lot there. All right, so we got 22. So we got negative, this here is negative 8, or negative 10, I mean. And this here is 4. I'm just labeling the coordinates that we're actually interested in. 8 and 22. So, and let's do the y's. So y's are to negative 4. 1, 2, 3, 4. So when x is negative 10, y is negative 4. Just looking at that coordinate. When x is 4, y is negative 3. When x is 6, y is negative 2. And then when x is 8, y is negative 1. And then when x is 22, y is 0. So we have our graph. So it looks something like that. So if we look at the original parent function, right? Normally we have 1, 2. Normally it looks like 1, 1, and then 8, 2, 0, 0, negative 1, negative 1, negative 8, negative 2. So normally it looks something like this. So this is how normally the parent function looks like. So what happens to the parent function? Well, it got shifted, right? It got shifted, looks like to the right. Let's see, by how much here? If we really look at it, looks like it got shifted to the right by 6. So if we look at this right here, right? This right here is the same thing as 2x plus 6. So it looks like it got shifted to the right by 6. All right, and then it looks like it got shifted down 2 because of that negative, right? So it got shifted down 2. So we got 1, 2, and that's why we're over there. So that's the transformations there. And then it also got, a little bit compressed, right? So it's not exactly the same shape that it was before because of this 2 here. So it got vertically, I'm sorry, not vertically compressed, it got vertically stretched because it's skinnier. Notice that the graph is skinnier than it was before. So it got, it's more stretched out, I mean. So it's more like that, it's stretched out than it normally is. All right, so that is it. We're going to go ahead and have you guys try. So pause the video, give the following problems a try, and then we'll cover the solutions. Alright, hopefully you paused the video and did not just wait for me to go over the solution. So you can actually give it a try. The best way to do this is to practice. So the first problem, square root of 3x minus 1 plus 2. Let's go ahead and set up a table for that. So this is a square root right here, so we're dealing with a square root function. So the parent function is square root of x. All right here, so now we have x, so since we're dealing with square root of x, we're going to choose x 0, 1, 4, and 9, because those are perfect squares. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, and square root of 9 is 3. So that's why we chose those values. Now, for the x transformation, we're going to set this equal to x prime and kind of just solve that. Let's do that off to the side here. X prime is 3x. I'm going to need some space here, actually. 3x minus 1. So we're going to add 1 on both sides to solve for x. We get x prime plus 1 equals 3x. Then we're going to divide everything by 3. All right, so this becomes x plus 1 over 3. All right, and then our y transformation, what is happening to the outside of the radical? We're just adding 2. So this is going to be y plus 2. Very simple once you get the hang of it. All right, so now when x is 0, we're going to plug that in right here. So 0 plus 1 divided by 3, that's just 1/3. 1 plus 1 divided by 3, that's just 2/3. 4 plus 1 divided by 3, that's 5/3. 9 plus 1 is 10, so 10 divided by 3, that's just 10/3. Those are just fractions. You can convert those to decimals if you like. So now for the y coordinate, we're just going to simply plug that in and then add 2. 0 plus 2 is 2, 1 plus 2 is 3, 2 plus 2 is 4, and then 3 plus 2 is 5. Right, now we are ready to graph. We got our coordinates. We should be able to graph this, no problem. So we got our y coordinate all the way to 5. We're going to stretch the x coordinates out a little bit so we have enough room. Okay, so when x is 1/3, y is 2. So 1/3 is pretty small, it's around here. So when x is 1/3, y is about 2. When x is 2/3, that's closer to 1, y is about 3. When x is 5/3, which is a little bit over 1, 1 and some change, almost 2, because 2 times 3 is 6, then you get a value of about 4. And then when x is 10, 10 divided by 3, 3 goes into 9 3 times, or 3 goes into 10 3 times, so it's a little over 3. So we're going to put a 3 here. So we got 3, a little over 3, and 5. And then we got our transformations there. All right, so we got our square roots function right here, and we are done. Now note that this is shifted to the right because we got a minus sign there, so that means a shift to the right, which makes sense here. And then we got a shift up because of that plus 2, so this also makes sense here. And then we got a slight horizontal compression, which is kind of hard to tell here, but it's present nonetheless. All right, so let's do our next graph. So we have x, y. This time we're dealing with a cube root, right? So our parent function is cube root. We're going to do our x prime, our y prime again. So now we're going to choose the cube root numbers, -8, -1, 0, 1, and 8. Okay, just like we did before. So the cube root of -8 is -2, -1, 0, 1, and 2. All right, so let's look at our x transformations. That's this guy right here. We're going to solve for x here. So this means we need to subtract 3 on both sides. So now we get x prime minus 3 equals -x. So we're going to go ahead and divide. What we're going to do instead, since this is a negative, I'm going to flip that into a positive. But if I do that, I need to flip these signs. Negative here, positive there. That's probably the easiest way to deal with those negatives, okay? So now we got -x plus 3. All right. So now we have the y transformations, what are we doing to the y, to the radical? Well, we're multiplying it by -1 and we're subtracting 4 to it. So that's exactly what we're going to do to y. Negative y plus or minus 4. Okay, just like that. All right, so now we have here -8, -2. So let's go ahead and plug in -8 into the x here. So we got -8 plus 3. Well, 2 negatives is a positive. 8 plus 3 is 11. Now let's do -1. -1 is 1. 1 plus 3 is 4. -0 is 0. 0 plus 3 is 3. -1 is -1. -1 plus 3 is 2. -8 is -8. -8 plus 3 is -5. Now we're going to plug in -2 in for y. So we get -2 take away 4. So we got 2 minus 4. So this is going to be positive. 2 minus 4 is -2. Now we got a -1. -1 is 1. 1 minus 4 is -3. Now we got a 0. -0 is 0. 0 minus 4 is -4. -1 minus 4 is -3 or -5. And then -2 minus 4 is -6. All right, so we got those numbers there. We got our coordinates now. We can go ahead and graph those. All right, so we have here all the way to x equals 11. 1, 2. And then we have x equals, so 1, 2, 3, 4, 5. So it's actually, this is actually 10, so 11. Okay, and then we got some negative numbers for x. We got -5, -3, -2, -1. And then for the y's, we got all the way to -6. All right, so we have here when x is 11, y is -2. When x is 4, y is -3. When x is 3, y is -4. When x is 2, y is -5. And when x is -5, y is -6. All right. So a funky looking graph, but remember we have this shape like this, right? And then this goes like this. So we have our characteristic cube root shape. All right, so this should make sense. Let's see if it makes sense. Well, we have a +3 inside here, which means it shifts to the, normally it would shift to the right, because it's, you know, the negative there, or because of that positive there. So normally actually, I'm sorry, if it's plus in the inside, this means left, right? However, because of that negative actually makes it shift to the right because it's a reflection. So if it shifts to the left 3, since it's reflected, it's really to the right 3. So that's a little bit of a technicality there. But either way, it shifts to the right 3 because of that. And then it shifts down 4. 1, 2, 3, 4, you can kind of tell. So that kind of makes sense. And then we got a reflection. That negative means you're reflecting it, so it's a reflection about the x-axis there, and this is a reflection about the y-axis. So it does a couple of reflections, and that's about it. That's our final graph. All right, that's it for the end. That's the end of the video. I hope you learned something from this. There's a lot going on to graphs, but at the end of the day, once you learn this table method, you can graph really any type of transformation. And I'll see you guys in the next video.